Today, the first speaker is Inti Sodemann, and he's going to tell us about shear sound and universal shear conductivity of Fermi seas. Floor is yours, Inti.
Yeah, thank you very much to the organizers for this opportunity. Thank you all for coming. So let me begin first by apologizing. So this talk will not be about quantum Hall physics, but I think the topics are close to the heart of many people in the audience, and also the platforms in which some of the effects I'll describe can be seen are actually the same two-dimensional electron systems in which quantum Hall physics is studied often. So I think it will be also of interest to experimentalists here. But yeah, apologies to the organizers and to the audience for violating a little bit the rule. Yeah, so I'll be talking about basically two stories, and they are connected to each other by the word shear. So I will be talking about shear or transverse fluctuations of quantum Fermi fluids, but the stories are different. And this is work done with in collaboration with a few young people. Gianni, who is now at Singapore, Po Yao, who is at Tsinghua in Taiwan, Falco in Frankfurt, and Suraj, who's in Max Planck in Dresden. So let me motivate what I'm going to tell you first by considering what are the regimes of electron motion, of collective electron motion. So imagine you are probing the electron fluid at some length scale, at some distance L. You can imagine this as some type of perturbation that you're applying to the system that has some typical length or wavelength L. And so, roughly speaking, the behavior of electrons falls into three different regimes. One is a regime in which the perturbations that you're applying change over length scales that are much longer than the mean free path. And in that regime, basically, you just get diffusion. This, for example, the regime that is probed mostly in transport. If you manage to perturb the electron fluid over length scales that are smaller than the mean free path, then you will have essentially conservation of momentum. And over those length scales, there will be an emergence of essentially classical hydrodynamics. So you still need some equilibration. So the idea is you will be probing the electron fluid over some length scale that is larger than the electron-electron collision length. And you will see essentially sort of the behavior of classical fluids. But if you manage to probe the electron fluid over shorter length scales, smaller than the electron-electron collision mean free path, then you will enter a third regime, which is truly what I would call the quantum hydrodynamic regime of the collective electron motion, which is described by Landau theory. And this regime has been explored maybe in helium-3, but I would say from the point of view of dynamics, there's very little explorations of this regime in solid state. And the reason, to a large extent, is that materials often have are not sufficiently clean. Most of the probes that you apply, for example, in transport, are electric fields that change over very large length scales. So you rarely access this regime experimentally in solid state. But there is a lot of interesting physics and unexpected physics that can happen in this regime. So this talk is going to be basically about two stories of things that you can see in this quantum hydrodynamic regime. So the first part will be about a new kind of collective mode that is a shear sound mode. And the second part will be about some response function that we call the universal shear conductivity that, as I'll show you, it applies not only to electron Fermi fluids, but also to spin-on Fermi fluids, and it takes a remarkably universal form that it's only controlled by the shape of the Fermi surface. So why is it that there is a new regime? What is the principle behind it, let's say? The idea, in a sense, is that whenever you cross each of these length scales, you gain new conservation laws. So when you're in the ohmic regime, basically the physics is dictated by the fact that the conservation law at length scales above these length scales is just the particle number. Electron charge does not disappear, but everything else relaxes. When you enter the shorter wavelength regime, the shorter length scale regime of hydrodynamics, then the momentum conservation emerges as a new conservation law, so something that cannot relax locally. But when you go, to even shorter length scales, and you access the Landau Fermi liquid regime, really what happens is that you gain an infinite number of conservation laws, so to say. And these are not microscopic conservation laws. They are not sort of exact microscopic laws in the Hamiltonian, but they are emergent conservation laws that arise because of the long lifetime of the quasi-particles. So essentially, you can think of this Landau Fermi liquid regime as some regime in which the shape of the Fermi surface itself becomes a slow variable. And so to describe the shape of a Fermi surface, the formations, you need to introduce an infinite number of quantities. So let's say the expansion will be, the local expansion of the Fermi surface will be the density that you have in the diffusion case. The L=1 deformations will encode the currents, but there is also many other quantities that become slow. For example, the amplitude associated with this nematic L=2 deformation of the Fermi surface will become a slow mode as well in this regime, so to say. And this is the principle of why this is really a new hydrodynamics. It's a quantum hydrodynamics, which is, essentially quantum Landau Fermi liquid theory. And so the idea of this first part is that there is some, just to illustrate the kind of very sharp new qualitative phenomena that can emerge in this regime, let us consider the behavior of transverse currents. Okay, so imagine you prepare some initial condition. Okay, let's not ask exactly how for a moment, just hypothetically. Imagine you prepare some initial condition of a fluid, so there is some transverse, profile of the current. So these white arrows here are meant to be the current of the electrons. So the electrons are flowing in this fashion as an initial condition, let's say, with some length scale, some wavelength L, okay? So if this length is larger than the electron-electron mean free path, these currents are going to decay, locally. They're going to disappear locally because of the friction that the electrons are experiencing from impurities. So there's going to be just basically some finite decay time for the amplitude of this perturbation that is controlled by the mean free path. When you make this length scale, this wavelength of this initial condition, let's say, shorter than the mean free path, so that you're in classical hydrodynamics, you still get decay. So the currents just, eventually die out with time. But what happens is that the decay becomes very slow, simply because you cannot lose currents locally. The electrons are just exchanging momentum among themselves, so they're not losing it to impurities. So this manifests itself with the following property. So the time it takes to decay this transverse current grows with the length, with the initial wavelength, just because you cannot, it cannot disappear locally, so it needs to be transported from one side to the other in order to sort of annihilate it. So the decay time grows, and this is the manifestation, let's say, of the classical hydrodynamics, let's say Navier-Stokes equation. But what I'll show you is that when you're in this quantum hydrodynamic regime, the electron fluid can actually develop a restoring force for this type of perturbation. So you will actually see some oscillations of the transverse current that are long-lived, and the lifetime of those oscillations or the decay time actually diverges as you approach zero temperature. Eventually, it will be cut off by mean-free path, but ideally in the clean limit, it will diverge at zero temperature. You know, very, very weak amplitudes, let's say. And this is very interesting because it's not usual that a fluid will have shear, you know, long-lived shear sound-like modes. Shear modes are characteristic of solids, and basically they are protected in solids by the existence of a shear modulus, so some restoring force to this type of shear deformations of the solid. So the solids will have two types of sounds, you know, some longitudinal or compressional and this transverse sound. But the idea here is that we will have two kinds of sounds for the electron fluid if this you know, shear sound is present. So you will have the plasma mode, which is sort of the analog of this compressional sound mode in solids. But in addition, you will have some mode that is purely transverse, and you know, it doesn't have charge density fluctuations. It's only transverse current fluctuations, which is this shear sound. Now the caveat is that while the plasmon or the longitudinal sound, the zero sound, what would be the zero sound, appears in a Fermi liquid for arbitrarily weak interactions, the shear sound actually requires a threshold. So weakly interacting Fermi liquids, you know, weakly repulsive Fermi liquids always have a plasma mode, always have a shear, a compressional sound mode, but they will not have the shear sound mode. So the shear sound mode will only appear if the Fermi liquid is sufficiently strongly interacting. It will only appear as a sharp collective mode. And this criterion can be translated into the as follows. So the mass of the electron fluid needs to renormalize beyond some threshold, essentially. That is, needs to be larger than two times the bare mass. And 3D is a bit more demanding, so you need to go to stronger interactions. But beyond this threshold, then this mode will become a sharp collective mode outside of the particle Hall continuum. And so, you know, this prediction can be made within traditional Landau Fermi liquid theory. I am going to present a slightly, you know, more modern version of Landau Fermi liquid theory that will be useful also for the second part of the talk. So let me kind of give you a crash course of Landau Fermi liquid theory here. Yeah, so Landau Fermi liquid theory, it's a very beautiful theory. So it's a theory in which you essentially promote the shape of a Fermi surface to be a dynamical variable, a variable that makes sense locally in space and time. And you're describing the fluctuations of the shape of this Fermi surface. So in its original formulation, let's say it's a classical theory of this shape. Okay. So, you know, the shape can be decomposed, the deformations of the shape can be decomposed into harmonics, angular harmonics, and there is some kind of stiffness coefficient or, you know, energy cost for the amplitude, the deformation of a Fermi surface in each of the harmonics, and that's what it's Landau, characterized by the Landau parameters. There are a sense of stiffness associated with each of these deformations. And so you have a bilinear theory, right? So there's an energy associated with the deformations, and it's a bilinear functional of these deformations. And there is a kinetic equation. There is a differential equation that comes together with this energy functional, which is the Landau kinetic equation. And one can put this equation in a Hamiltonian formalism by introducing some Poisson bracket for this Fermi radius variable, as described here. So basically what I'm writing here is just really just take the textbook Landau Fermi liquid theory, just a slightly different way of viewing it as a canonical theory. So the Landau energy functional is a Hamiltonian, and then there is some Poisson bracket for the Fermi radius field and some classical equation of motion, which is just another way of rewriting Landau kinetic equation. So once you have that, it's natural to promote the Fermi radius. Then if you want to view the theory as a quantum theory, to promote the Fermi radius to an operator. So everything that was a classical field in the previous slide, now we will just put hats on it. So it's an operator to promote this Landau energy functional to a Hamiltonian, and the Poisson brackets to commutators. And so basically you end up with some algebra for the Fermi radius operator, which is just essentially a very natural generalization of the algebra that you have for 1D Latinger liquids, except you can think of the angle at which you have the deformation of the Fermi surface as a label for different Latinger wires, so to say. And these ideas were introduced by Haldane, Eduardo, and many others. And more recently, I think this sort of perspective of this bosonization as essentially a quantization of Landau Fermi liquid theory was explained very nicely, some papers by Son. And so, but the nice thing is this is a bilinear theory. It's a theory of harmonic oscillators, essentially. It's a quadratic theory on these bosonic fields. These are bosonic fields. And so you can solve it exactly, right? So there is a very precise correspondence between solutions of the classical kinetic equation and this quantum version. So there's a one-to-one correspondence between classical and quantum modes, just because it's a bilinear theory, just similar to what happens in the harmonic oscillator. And so basically one can organize the different fields that appear, which correspond to different deformations of a Fermi surface with different harmonic deformations of the Fermi surface, of the 0, the 1 harmonic, and the 2 harmonic. The fields forms some coupled structure. And basically what you can show is that you can, by solving a tight binding model, a classical tight binding model where the sites correspond to the amplitudes of the deformations of the different harmonics of a Fermi surface, you can get basically all the modes of the theory. So the Landau parameters appear as disorder in this picture. So there is a site, each site is a different angular momentum deformation of the Fermi surface. And the Landau parameters appear as a modulation of the hopping between the sites. So, it's a chain. So you will get then in the non-interacting case, the chain is translational invariant. So you get a continuum. And that continuum is just basically a different way of describing the usual particle-Hall continuum. But you can also get impurity states, so to say localized modes associated with the bond disorder from the Landau parameters, and those are the collective modes. So from this picture, it's actually not very surprising that there is other possible collective modes beyond the zero sound or the plasma mode. So what you encounter is, in particular, for the first transverse mode to exit the continuum to become a bound state, this Landau parameter needs to increase above 1. So then it exits the continuum and becomes a sharp mode. Okay. So, just to kind of summarize, so the picture more or less is there are solutions to the kinetic equation. Some of them are localized in the angular harmonic deformation space. So those are the conductive modes. So they have a wave function in this chain picture that is exponentially localized around some mode, some site, let's say, which would be like a L equals 0 deformation. And there is some plane waves in this chain. Those delocalized plane waves in angular momentum are sharply localized in angle deformation. So those are the particle-Hall excitations of the continuum. And so this shear sound appears, but you might ask, how to reconcile the appearance of the shear sound in certain Fermi liquids with the fact that the system has to be a liquid. It does, it should not really have a shear sound at extremely long wavelength. So basically, this slide is just to try to explain how to reconcile this with the classical fluid behavior. Okay. So what happens when you solve the kinetic equation in the presence of electron-electron collisions is that, assuming that the shear sound would be present in the absence of collisions. So what happens now when you add collisions is that there is actually a branch at very small q, which describes the hydrodynamic, Navier-Stokes diffusion mode. So at very long wavelengths, the currents will decay. But this window over which the fluid behaves essentially as a Navier-Stokes fluid shrinks to 0 as you lower temperature. So as you cool the Fermi fluid, then this extra branch, that is the propagating, oscillating branch, the shear sound branch, goes to exists at an increasingly smaller q. Okay, so it becomes it's another branch. It's different from the shear Navier-Stokes branch, which becomes closer and closer to small q and small omega as you cool off the Fermi fluid. And this mode has not been seen in experiments. Okay, so there is some proposal that we made in order to see it. I'm going a bit slow in time, so let me skip a few details. And the proposal is basically that if you take a two-dimensional electron gas, you imagine you have some electron gas, and you have this electron gas flowing in some channel that has some width W. There will be some geometric resonances for the flow of the electron fluid as you try to pass it through the channel. So imagine you're driving this electron fluid with some electric field at some AC frequency omega. There is going to be a geometric resonance. And so when you hit the resonant value of the shear sound mode in this channel, what happens is there is a dip in the AC conductivity. This plot is a plot of the conductivity of this channel as a function of frequency. So so the net conductivity, you're sort of trying to flow the electron fluid through this pipe, so to say, and then you will see these resonances at specific frequencies. Okay, and I think this is within reach in two-dimensional electron gases, especially those with small masses, those that are easier to drive closer to the Wigner crystallization transition. Okay, so as the electron fluid is approaching the Wigner crystallization transition, it hardens, and then this shear sound mode exits, and then you might see these resonances. So here, for example, are some estimates for the zinc oxide, magnesium zinc oxide heterostructures. So basically, the criterion is you need to, the effective mass of the quasiparticles needs to be twice the bare mass. So you need to drive it closer to the Wigner crystallization transition to see the enhancement of the quasiparticle mass above this value, but you're still in the Fermi liquid. It's not the Wigner crystal. It needs to be clean. So this width needs to be, comparable or shorter than the mean free path. And you need to be at low temperatures to access the quantum Landau Fermi liquid regime. So this typical temperature, let's say, for this heterostructure. And then, the challenge is at finite frequency. So for this particular system, you will see the first resonance at about 0.1 terahertz. That's our estimate. But it should be doable. It might be also possible to do it with weak magnetic fields that might open up coupling between longitudinal modes that you could excite, let's say, with near field techniques. So if anybody has like SNOM type near field techniques that have been used to image plasmons and can do it with magnetic fields, please let me know and we can chat some more. But let me with that move on to the next part, and I'm a bit short on time, so I'll try to be very quick here. So the second part is about a universal response that we have found for spin-on Fermi surfaces and electron, Fermi liquids. And so it's in a very different regime than the regime I was just talking about. I was talking about sort of, collective modes outside of the particle-Hall continuum. But the statement, these now are in the regime of very low frequency, so near this part of a particle inside the particle-Hall continuum. So the statement is that the transverse electric conductivity at finite Q, but in the limit of omega going to 0 here, it's a completely universal quantity that only depends on fundamental constants of nature and the geometric shape of a Fermi surface. It does not renormalize by the strength of interactions. It doesn't know about the quasiparticle mass. It's just, this controlled by the size of the Fermi surface, okay? And so very briefly, this is a result that is meant to apply both to electrons and spin on Fermi surface states. It's the electrical conductivity. So let me just, very briefly flash what the spin on Fermi surface state is. Spin on Fermi surface state is a spin liquid state in which the electron fractionalizes into a neutral fermion, the spinon, and a boson, the chargon. The boson carries the charge and it's sort of frozen. It's not there at low energies. You only have the spinon making up a Fermi surface state. The two particles are coupled by a strong, U1 gauge field, an emergent photon. Okay, it's a state that was, conceptualized since pioneering work by Anderson. It's been controversial whether it's in materials, but there is a few potential candidates where one could look for the state. And what I will present to you can be understood as follows from the following type of formalism. So imagine we start with some field theory that is describing both the spinon and the chargon. Chargon is making a Mott insulator, is gapped, so we can integrate it out. We get a Maxwell action. For the important thing is that it's for the difference of the emergent electric field, that is this little e, and the physical field, that is this capital E, and the emergent magnetic field is this little b, and the physical magnetic field is this little b. And so here, even after integrating out the chargons, you have spinons in a Fermi surface coupled to a U1 gauge field, so it's still a strongly coupled problem. So what we will do is we will bosonize this spinon Fermi surface state in the same formalism that I was just using for the Fermi liquids. And so we have a gauge theory, a gauge version of that bosonized theory I was just presenting to you. So this Lagrangian here is just meant to be the bosonized description of the Fermi surface fluctuations coupled to a U1 gauge field with this type of action. So that's the context and the results that I'll present. But I just very briefly want to say that I think there is a bit of a misconception that is relatively widespread, that is the following. So is this a system of Landau Fermi liquid or not? So often Landau Fermi liquids are defined by having a finite residue for the quasiparticles. So the spinon doesn't have a residue. It has a very large also self-energy, imaginary part of self-energy. So there is no well-defined spinon quasiparticle in some sense near the Fermi surface. But what is known is that the particle hole excitations of the spinon Fermi surface actually behave as a Landau Fermi liquid. So there is a generalized sense of a Landau Fermi liquid in which you can have no residue, so no Landau quasiparticle itself, but the gauge neutral particle hole pairs are behaving essentially with the same kinetic equation as the Landau Fermi liquid. Okay, so in that sense, this system is still a Fermi liquid for the gauge neutral particle hole objects. So that's basically the rationale behind what we're doing here. So we essentially have just a gauge version of Landau Fermi liquid theory, coupled to this U1 gauge theory. I'm sort of out of time, so let me not go to too many details, but it's basically just the formalism I presented for Fermi surfaces, but now coupled to gauge fields. And so we can do calculations with that. And if you just compute the conductivity at Q equals 0, which would govern, let's say, optical absorption and also a transport at very small omega, what you find is the following. So, in the electron, the blue is for the electrons. So the electrons, will have a Drude peak in the conductivity. They are metallic. The spinons do not have Drude peak. They have a power law. They have some resonance at high frequency that is essentially the optical gap, as an optical pseudo gap. So from this point of view, they look like insulators. But the remarkable thing is that if you go down the particle hole continuum at finite Q, they actually approach the same limit as the metal, the same universal limit that I referred. This limit that doesn't, for the transverse conductivity. Sorry, let me slow down. So the transverse conductivity has the same limit at finite Q when omega goes to 0, both for spinons and metals. So this blue line is for the metal, the red line is for the spinon. The curves are different, but the point is the limit at very small omega is the same. And this limit is universal. So you need to be in the condition in which you're probing Qs that are above the inverse collision mean free path. But the result is actually general, even if the Fermi surface has a very weird shape. So this is the more general formula. So in this limit of omega going to 0 at finite Q, the transverse conductivity doesn't know anything other than the shape of a Fermi surface. And so basically at a given Q, the formula generalizes to the as follows. So you take the Q, you find the spots at the Fermi surface that are tangential to the Fermi surface, in the direction defined by that Q. You measure the local radius of curvature of a Fermi surface at each of those spots. So there's a finite number of them. You add those radii and divide by 2Q. Okay, so it always knows only about the shape and it doesn't change with interactions or the mass or anything else. I am essentially out of time, I think. So I was going to give you some intuition of how this is possible, because this is very weird, right? It's an insulating state, but somehow in this channel, it looks like a metal. Let me skip that. And let me just say that a very good way to probe this in experiments, because it's a very hard regime to reach, is with MV center spectroscopy. So by monitoring essentially the noise, the magnetic noise that comes out of the sample. And so what you can show is that in this regime, the magnetic noise, the autocorrelator of the magnetic field, is also universal. So it only depends on the perimeter of the Fermi surface times some combination of fundamental constants on nature times omega divided by Z, where Z is the distance at which you are probing the noise. So this is something that is within reach of MV center spectroscopy techniques. And with that, let me leave you here with the summary slide of these two things. Thanks for your attention.
Okay, thank you very much. So I guess we have to move on.